From last week's content, let's recall our weak form equation as shown here, which is simply negative of e times integration over the domain of w comma x ux dx plus the boundary term, which is e times the weight function w times u comma x evaluated over the boundary represented by partial of omega plus the force term. Okay, so let's assume an approximation to our displacement. Okay, approximation to the displacement u of x. Let's say u of x is equal to some function phi0x plus c1 times phi1x plus c2 times phi2x. Let's say we have n such function, cn times phi n x. As we know that the weak form satisfies the natural boundary condition. Right, which is u comma x in this term right here. Then the approximation of u of x need to satisfy the essential boundary conditions. Okay, for example, if we have a prescribed displacement at x is equal to L, let's say it's some displacement g. For convenience, let's try to divide the assumption of u of x into two segments. Okay, one segment is phi0 of x and the other segment is the rest of the functions. Okay, and let's write that down once more in a more compact form. So u of x is equal to phi0 of x plus summation over all the i's varying from 1 to n, coefficient ci times the function phi of x. Okay. Now for convenience, let's say our phi0 of x need to satisfy the prescribed displacement boundary condition. That is the essential. And let's say rest of the phi's will be 0 wherever the essential boundary conditions are defined. Okay, so reconsider our previous example where u of L was equal to g. Then following these assumptions here, you can say that the phi0 at x is equal to L will satisfy the value of u of L, it is equal to g, which is equal to g, right? And rest of the phi's at L would be 0. So now let's substitute u of x in the weak form. So then we can write negative e times the integration over the domain omega wx. Then in the bracket you can say this is phi 0 plus summation over I of ci phi I and the differentiation of the whole bracket with respect to x d omega plus the boundary terms, which is e times w times ux evaluated at the boundary, plus integration over the domain omega w times the force d omega is equal to 0. Okay, now let's simplify this equation further. Let's write these two terms separately. Okay, so that will end up being minus e times integration of wx phi 0x d omega minus e times integration of wx summation of ci phi x dx, and the rest of the term follows as the following. Okay, now let's notice a couple of things in this equation right here. Since the phi 0 of x satisfies our essential boundary condition, we would know this term beforehand. Okay, over here for a given weight function, we will have either the prescribed traction boundary condition or the displacement boundary condition. So we can also evaluate this term, and we will know the force as a function of x. For a given weight function, this term is also known. So marking this term like this, all the terms with the blue mark are known terms. Now consider the second term here, where we have unknowns, which are the coefficients ci's to the function phi I. So for a given weight function, all the coefficients are the unknowns. Okay, so let me specify them. These are knowns. And the second term is an unknown. So it boils down to solving for the coefficients ci's. Okay, so since we have n coefficient ci, we'll need n equations.